July 26, 1875, 10:47 a.m. Cheshire, England. Edward Leader Williams stands at the edge of an impossible problem. Below him, the Trent and Mersey Canal flows at 50 feet above the River Weaver. 50 feet of vertical nothing, and somewhere in the mathematics of that gap lies either his reputation or his ruin. The boats waiting below carry salt, tons of it, mined from the Cheshire earth, destined for markets that will pay premium prices if it arrives fresh. But those boats can't fly. They can't climb stairs. They need to rise 50 feet through solid air, carrying their cargo intact without spilling a single grain into the water below. Williams has been the chief engineer for the Weaver navigation for 2 years. 2 years of watching profits drain away because boats take the long route. 2 years of watching competitors laugh at the absurdity of it all. How do you lift 250 tons of water and boat and cargo straight up like pulling a curtain? The traditional answer is locks. Build a staircase of 15 chambers, each one lifting the boat a few feet higher. Gate after gate, valve after valve, fill, wait, drain, repeat. The engineers call it proven technology. Williams calls it surrender, because 15 locks means 3 hours. 3 hours means 30 boats per day maximum. 30 boats means Cheshire salt rotting in warehouses, while Liverpool merchants buy from competitors who don't have vertical geography problems. He's done the calculation 17 times. The numbers always tell the same story. Locks are too slow. Inclined planes, dragging boats up rails, would shred wooden hulls like paper. Everything conventional is wrong. So Williams sketches something unconventional. 2 water tanks, each one 75 feet long, 15 feet wide, filled with water deep enough to float a fully loaded narrowboat. Connect them with massive cast iron troughs that form a perfect rectangle, top and bottom chambers balanced like a scale. When one tank rises, the other falls. Not with pumps, not with engines, with something older than machinery, gravity. But here's where it gets strange. The descending boat is heavier. It's coming down full of cargo while the ascending boat floats empty. Physics says this shouldn't work. The heavy boat should plummet while the light boat stays stuck at the bottom. Williams adds one elegant detail that breaks the symmetry: hydraulic rams. Not to lift the boats, that would take enormous power, but just to add weight to whichever side needs it. Press water into a cylinder beneath the lighter tank. The weight shifts, the balance tips. The lighter boat, now artificially heavier, descends. The cargo-laden boat rises. It's Aikido engineering, using the enemy's weight against itself. The board of directors hears his pitch on a Tuesday. They ask how much it costs. Williams says 48,500 pounds. They ask how long it takes to move a boat. Williams says 5 minutes. They stare at him like he's proposed teleportation. 5 minutes to move 250 tons up 50 feet? Correct. Using water pressure and gravity? Correct. No steam engines? None. The room goes quiet. Finally, the chairman speaks. If you're wrong, Williams, this will be the most expensive garden ornament in England. Construction begins in spring. They excavate 2 massive pits, 50 feet deep, perfectly aligned to millimeter precision. The slightest misalignment means the tanks won't seal. A broken seal means catastrophic flooding. There's no room for approximation. The ironwork comes from Neath Abbey, Wales. 75-foot cast iron troughs each one a single piece shipped by barge because nothing on roads can handle the weight. When the first trough arrives, it takes 40 men and a custom-built crane just to position it. The hydraulic cylinders arrive next. Each ram is 3 feet in diameter, 9 feet tall, capable of pressing with 700 tons of force. They're installed in massive brick chambers beneath the lift, connected by a labyrinth of pipes that must never, ever leak. Because here's what people don't understand about Victorian hydraulic systems. They run on water, yes, but at 800 pounds per square inch. That's not plumbing. That's controlled violence. One failed seal doesn't drip. It explodes. It shreds iron. It kills anyone standing nearby. Williams inspects every joint personally, every rivet, every gasket. The construction crew thinks he's paranoid. Williams thinks they're underestimating water pressure by about 790 pounds per square inch. June 1875. The structure is complete. 2 iron tanks hang suspended in their pits, connected by hydraulic rams and a prayer that physics works the way Williams calculated. Now comes the test nobody wants to watch too closely. They flood the upper tank first. 252 tons of water rush in. The iron holds, the seals hold. So far, nobody's dead. They flood the lower tank. Another 252 tons. The balance shifts. The tanks settle into equilibrium, upper and lower, waiting for the signal that tells them which way to move. Williams climbs down to the hydraulic chamber. The control valves are simple. Open one, close the other. Route water pressure to the correct ram. Create imbalance. Let gravity handle the rest. He reaches for the valve wheel. A worker grabs his arm. "Sir, perhaps someone else should." Williams shakes him off. "If it fails, I want to be standing here when it does." He opens the valve. Water hammers into the hydraulic ram beneath the empty upper tank. The pressure gauge climbs. 200 pounds per square inch, 400 pounds per square inch, 600 pounds per square inch. The upper tank, now heavier than the lower, begins to descend, not lurching, not grinding, smooth as breath. The lower tank rises. 50 feet of vertical travel happens in 150 seconds. The tanks pass each other at the midpoint, upper becoming lower, lower becoming upper. The whole massive mechanism moving like it weighs nothing, because functionally it does. The 2 tanks are hydraulically balanced. The only weight the system moves is the weight differential. The cargo in one boat versus the emptiness of the other. A 50-ton load moves with the energy required to overcome maybe 5 tons of resistance. Williams exhales. He's been holding his breath for 150 seconds without realizing it. The Anderton Boat Lift opens to commercial traffic on July 26, 1875. The first boat carries salt, obviously. The captain is terrified. He spent 20 years on canals, moving horizontally. Now some engineer wants him to float into an iron box and trust that he'll arrive 50 feet higher without plummeting to his death. But he needs to deliver this salt, so he steers into the lower tank. Workers close the watertight gates behind him. The captain grips the tiller so hard his knuckles go white. The tank descends. For 2.5 minutes, he floats inside a moving elevator, water sloshing gently against the iron walls. Then daylight appears ahead. The upper gates open. He's at canal level. 5 minutes total, cargo intact, boat undamaged, captain alive but needing a drink. Word spreads fast. Within a week, boats line up at both levels. The lift operates 18 hours a day, moving boats up and down with mechanical indifference. It doesn't care about weather, doesn't care about weight distribution, doesn't care that what it's doing shouldn't be possible without engines. The 15 locks sit abandoned, useless overnight. But here's where the story gets strange. The Anderton Boat Lift isn't revolutionary, it's evolutionary. Williams didn't invent new physics. He just applied old physics with surgical precision. Every element, hydraulic rams, ballast tanks, pressurized water, existed before 1875. What Williams did was combine them with mathematical elegance, creating a system where the only energy input is the tiny amount needed to tip the balance. Everything else is gravity and water doing what they've always done. It's brilliant because it's boring. No innovation, no invention, just ruthlessly efficient application of known principles. And that boring brilliance runs for 108 years, through 2 world wars, through the rise and fall of British industry, through economic collapses and technological revolutions, while steam gives way to diesel, diesel to electric, electric to digital. The Anderton Boat Lift just keeps lifting boats with water pressure and gravity. By 1983, the ironwork shows its age. 108 years of hydraulic pressure has done things to metal that metal wasn't designed to endure. The seals leak, the rams stick. The control valves require percussive maintenance delivered with hammers. British Waterways faces a choice: scrap it or save it. That the lift has been obsolete for decades. Road transport killed the canal cargo trade in the 1950s. Nobody moves salt by boat anymore. Nobody needs a 50-foot elevator for vessels that barely exist. But 200,000 tourists visit annually. They come to watch Victorian engineering do its job with zero electronics, zero computers, zero anything invented after 1875. They come to see physics perform like it's 1875 and nothing has changed. British Waterways spend £7 million on restoration, not replacement. Restoration. They want the same hydraulic system, the same iron tanks, the same gravity-based operation. Because the Anderton Boat Lift isn't just functional, it's proof. Proof that engineering doesn't require complexity, that solutions don't need electronics, that sometimes the answer is water, iron, and mathematics applied by a man who understood that the best machine is the one that uses its enemy's strength. The restored lift reopens in 2002. It still takes 5 minutes to move a boat 50 feet, still uses gravity and water pressure, still operates on principles that would make sense to Edward Leader Williams if he walked up tomorrow. Because good engineering doesn't expire. It just keeps lifting boats through vertical space, indifferent to the passage of time, patient as geology, waiting for the next cargo that needs to rise.